Welcome back to emulating RISC-V in a high-level programming language. The series has come to the point where we are almost finished with the base implementation of the RISC-V instruction set. But there's one very important instruction that we need to implement before we can truly consider this to be a viable emulator. And this is how a program communicates with the environment in which it runs. Now, unless you're developing on a very low-level embedded device, you typically want to consume services that are provided by your operating environment, such as an operating system. For instance, you might want to open a file or read from an opened file or write to the screen or connect to a network server, any number of these services that are provided to you by the operating system. And naturally, on very low level devices, you could implement this yourself by reading and writing from the network card. But in general, you want to rely on the work of other programmers who already did this job for you. Also, we can't allow programs to have unfettered access to the hardware of the device because that would cause serious problems to occur if your program was malicious or had bugs in it. For instance, I'm not sure if I could write a file system driver correctly and then correctly access the individual blocks of a disk device. So to protect my program from the other programs and to protect the other programs from my program, we introduced this barrier in modern computers where you have a protection boundary between your program, which is running at a protection level, and the operating system or the operating environment, which is usually run at a higher protection level. And so you cannot access or look inside the code that is the operating system code, and that will limit the damage that you can cause. However, we do want to be able to expose services from the operating system because we do want to open files and write files and so on. And so there's a mechanism called system calls where when your program wants to make a call to the operating system, it issues a specific kind of call that tells the CPU that you want to transition to the operating system and have it continue in a highly privileged mode. So let's take a look at a very, very simple example of such such an interaction with the operating system. And we will go back to our program and then start sketching what this would look like. We're going to comment out the previous code that we had from last time. And then let's write a fragment in the C programming language first, just to make it a little easier to understand what we're trying to do. So here is a very small C program. What we want to do is we want to call the write function, which writes bytes to a handle. Now, a handle is the abstraction of an open file, and typically it's on most operating systems that support the POSIX standard, it's just a number. And some of these numbers have predefined meanings. Again, it's a convention that everybody has agreed to obey. And normally the handle 1, which is called the standard output on POSIX environments, that is the place where text messages get displayed when you call write or printf that sort of a message will use the standard output, which is handle 1. So what I'm doing here is I'm writing a little message. I'm going to create a little message, and the typical one to write is hello world. And we have to be sure to count the number of bytes. So this is 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3. So it's 13 bytes. So what this does is it tells the operating system I would like to write from the buffer message 13 bytes to the standard output whose handle is 1. And then at the end, I want to tell the operating system that I'm done. Please terminate the program and report the exit code 0 to the environment. And this number could be used to indicate other status codes, success or failures as you desire. So this very simple C program is what we want to do now in our little emulator. But there are a few things that we have to discuss before we can actually write this code. And the first one is how do you contact the operating system from our program? Now previously we've been using the JAL instruction to jump and link to another function in our code. But in this case, we don't know really where the operating system code is located. In fact, from the perspective of this program, the operating system code is not even visible. So we need a special instruction that lets the operating system know that we're willing to, or we're wishing to, consume a operating system service. Please perform that service for us. And that instruction in RISC-V is called ecall, for environment call. And it's a very simple instruction. It takes no arguments at all. And what it does is it triggers what is known as a trap. So when you execute that instruction, a trap happens in the CPU, and then a particular mechanism is invoked to start the supervisor code or the operating system code. And the operating system code will then look at who called it and try to determine what the caller wants by looking at the value of a register, perhaps. It might look and see that, oh, I've noticed that you set a particular register to a particular value, and that value will determine which one of the services that the operating system can provide. So we need to create a piece of code that will listen to this instruction and then transfer control to another piece of code that actually looks at the registers and decides, depending on which register, what to do. So that is one side of this. We have to create an emulator not just for the CPU, but an emulator for the operating system that we wish to emulate. And so we're gonna create a little mini operating system for the sake of the series, and we'll implement a few system calls to make that happen. The other concept, though, that we have to take care of is what about this message here? So far in our assembly language programs, we've only written code, but this is the first time that we're actually going to write some data. So we have to expose a mechanism for creating data and also a mechanism for referring to the data. And we will do that in this session as well. But let's start by implementing the exit operating system call, because that's the simplest one. It only takes one parameter, and it just stops the emulator. So how do we go about doing this? First things first, we need to implement this new instruction called ecall. So let's go to our mnemonics and add ecall. I'll put it in here. So the environment call instruction, and let's take a look at what the environment call instruction looks like when it's formatted. So you see that Well, let's go to the listing of these beasts over here. Where are they? There. So the instruction is eCall, and the eCall instruction is located here. So as you can see, it is a new instruction format type. Actually, it looks similar to the I instruction format type. Those are 12 bits exactly. So this is going to be another I type instruction. It has a new major opcode, and then all of the other fields, the RD, the funct3, and the RS1 fields are all zeros. So we will not need to provide any extra parameters to the eCall instruction. So let's go back to our code environment, and what we'll do is we'll go to the unit tests because we want to be rigorous about this. This is a new instruction. So let's go to the assembler and add a new unit test. I'm going to copy the scaffolding here, and we're going to call eCall the new instruction, and it will require, I'm not sure why the browser is behaving this way, but we will try to copy this. There we go. So this is the result that we want from an eCall. And so we will just tidy up this constant, and then eCall will have no variable or no arguments, no operands at all. Great, so let's evaluate this unit test, and it will fail. As expected, and now we get to implement this. So eCall is a new I style instruction, and the opcode, the major opcode is this bit pattern without the E. And its funct3 is 000, and the three operands are all ignorable, so we'll just send zeros. There's our eCall. Let's try running that, see if that satisfies the assembler. It does. So now we need to emulate eCall. So we go to our emulator tests, and we go to the end, and we grab the emulation of So how do we test that the eCall instruction was properly invoked? Well, what we can do is implement the exit system call, and what that would do is terminate the program. But we need to talk a little bit about how we select the exit system call. There's only a single place of extension here, the eCall instruction. So how do we tell the operating system that we want to call exit and not say open or write? Well, it turns out that you as the operating system designer have a choice on how to do this, and one way to do this would be to use one of the 8 argument registers that we have, X10, X11, and so forth, and designate that as the specific register used for selecting the system call. And we'll do this. We'll say that register X17 will be the one that is used to select system calls. So let's initialize register 17 to 0. Now 0 will be the system call used to trigger an exit. And then we will initialize register 10 to the value 1. And then after we call the system call, we're going to reinitialize register 1 to 42. But because this is the exit system call, the emulator is expected to stop executing. So if the emulation is done correctly, then this instruction would never get called. And so the value in X10 should remain 1. So this is our expectation, is that once we have executed this code, the value should not be 42, but 1, the one that we initialized here, and the one that stays in the register when we terminate the process. So let's attempt to run this unit test, and we're expecting it to fail. And indeed it does. And the reason why is because we haven't implemented this new opcode. So let's go ahead and do that. And this is the system call opcode. So now we need to go back and look at the immediate field, which is the field that starts at bit position 20 and is 12 bits long. We should have a bit field for that. Let's see. There it is, bit field immediate 20. So we'll use that bit field to extract the function, and that will be, how do we do this? We'll call this thing sys function, and it's going to be bit field 20 length immediate 20, extract, and let's extract an unsigned number from the instruction. And then we switch on the sys function. And if it's a 0, all zeros, then we're encountered an eCall function or instruction. And so what we do now is we are going to call trap to supervisor. Just like that. And break, and then a default handler for unsupported operations. And finally, we need to implement a trap to supervisor. So we need now to invoke a piece of code that knows how to talk to the emulator and find out what values are in its registers. So let's create a new class for this, because we need to implement an OS emulator, which is different from the CPU emulator. Now, the OS emulator could in turn start executing more RISC-V code, but it doesn't have to. In fact, to make our lives a little bit simpler, we're going to write this OS emulator in C#, and then we're going to invoke it from our machine code emulator to perform our services for us. So what does this OS emulator look like? Well, first of all, we need to think about what exactly it's supposed to do. When we trap to the supervisor, we're going to be given the current state of the emulator. So let's see, we'll call we will say public void trap, and then we're going to pass in the emulator itself, and then we might pass in the current state of the memory as well. Now this code will be called by our CPU emulator, and so in this emulator we will have the registers all set up. So all we need to do now is just check to see which system call was expected by the caller. So we'll say emu registers, and here is our convention. Register 17 contains the code for the operating system call that we wish to execute. Fine. Now we want to switch on that system call. And if it is the system call called syscall exit, and we'll define that as a public constant. If you ask for the syscall exit, then what we'll do is we will tell the emulator emu to stop. And we'll pass in the exit code, which was in register 10. So we will say emu registers 10. Actually, it's already there, so we need to extract the exit code from register 10 and then pass that on to the stop function. Great. And then for any other service, we will throw new not implemented exception, unimplemented system call, like so. Okay, and then we need to put a break at the end of this emulator, or this call. Okay, so the emulator which is an RV fun, needs a stop method now. So let's implement the stop method. And that should stop the emulator in its tracks. So let's go to the implementation of stop. Let's make it a public method. I'm not sure what my editor is doing here. Here we go. And so what we want to do now is find our main execution loop, which is in here, and we want to stop it. So we want to check for a condition that says that we have terminated. And we could do that right here. We could say if exit code has value, this is a new variable that I'm introducing, then return exit code value. Now, this is not particularly efficient because we're going to be checking for this exit code every time through the loop here. But for now, we are not focusing on performance for our little emulator. Maybe in a future session, we'll try to measure how quick it is and maybe find some way to improve its performance. But for now, all we're going to do is introduce this exit code variable. And the exit code initially is null. And then once we give it a value, then we break out of exec with that exit code. Let's put a comment here too as well that explains what this does. Execute RISC-V instructions until uh, told to stop. Nice. All right, so this while loop is never reached. But we'll just put a guard here just in case. So if we stop executing valid memory addresses, then we'll return -1. That means that we went off the rails and maybe started executing data. In any case, we want to register that as an error. Okay, great. So now we've done stop. So now trap to supervisor needs to call the OS emulator. So we want our we want our emulator to not only get an instance of memory, but also get an OS emulator to talk to, and we'll make that a member variable. Like so. And then we need to initialize the OS emulator field like so. Great. So now we have set up an environment for us to call, and then finally we're now going to call a method of the OS emulator. Like that. We need to pass a reference to ourself, and we need to pass a reference to memory. All right, so there's our code. And we are now ready to try this and see whether it actually works. So let's hop over to our unit test and give it a run. And this very likely is not going to work first try, but it's worth testing it. Okay, so we have a failure. No, we have a build failure. So what is the build failure? Ah, right. All the other places where we're creating the OS emulator, we have to create, or the instruction emulator, we now have to pass in an OS emulator. So let's create an instance of that. And here as well, we need to create an instance. Give it another shot. Okay, so we fail. What is the failure though? We haven't implemented stop. What's the problem? Oh, we haven't. Stop is supposed to set the exit code member variable to the value of exit code. That will cause it to stop. All right, try it again. There we go. So now we actually have implemented a very, very small operating system that all it can do is exit. And our emulator, when uh, well, it implements the ecall instruction to call the emulator, the OS emulator, and the OS emulator, in response to service 0, will get the return value. And let's actually verify that we get the return value back when we run. So let's go to our emulator tests and find, let's call this the exit code member variable. And then let's set up the exit code so that it has an exotic value that is unlikely to, well, actually, let's make it a nullable variable. And then in our code here, we will assert that exit code has a value, and that value should be the value 1. Let's run this again. Great. So we've confirmed that the 1 that we set up in register 1 is now the return value from the call to exec of the emulator. So we are now done with the interface between the user code that the emulator executes and the operating system service. But we would like to do something more interesting than just exiting. We would like to write a message. So we want, the next thing we're going to do is implement the write system call. And the write system call, if we go back to the program, takes 3 arguments. It takes the handle number, which is just an integer that describes which of the handles that the operating system is managing for us to use to write to, and then a pointer to a buffer, and then finally a size of the message in bytes. So how do we get a pointer though? Um, and so we can take a look at how this might look like in assembler language. Let's write a little assembler language variant or equivalent to this little C programming fragment. And the way we would do this is we would say, well, first of all, we need to set up the register 17 to the system call for write, which we haven't defined yet. So let's go ahead and do that. In our OS emulator, we'll create a new system call. Let's call that system call 1. And then in our program, we would set that into register 17. So we would say add I, again, used to initialize a small variable. And then add I would take 17 as its destination register, 0 and 1. And you know what? We can use the symbolic. We'll say os emulator dot syscall write. This is fine. We can use this constant, and this would be select the write system call. Next, we need to set up the arguments for the actual call. So x10, the first argument should be 1. 1 is the standard output handle. So register 10 should have the value 1. Use handle 1, standard out. The second argument, and we'll get back to this, we need to find the address of a buffer. So how do we get that? Well, we don't know, but we need an instruction that gives us the address of the buffer. So let's just call this address of and then message, and we'll come back to what that would actually look like. and that would be in register 11. So let's write that down, and then we will say x11 has pointer to buffer, and then finally register 12 will have the size of 13. X12 has number of bytes to write. Now we can call ecall, and we'll pass in the usual dummy variables, do the write, and then after that we want to exit with a 0 exit code. So we'll say add I to register x10, the number 0. We need to select the correct system call as well. '17 is our register for selecting that. Select the exit system call. And let's use a literal constant here again, just to be clear. And then we call ecall to tell the operating system that we want to exit. And from this point on, well, the emulator will stop here. We won't continue execution. However, we need a place to store the message that we want to write. So what we'll do is we'll add a functionality to our assembler to say, I would like to write a string into memory. So what we'll do is we'll say define string. DS is a commonly used constant or directive for assemblers, and we will give it the friendly string hello world. And then we also will note that in assembly language, if you don't specifically require a terminating null, which in this case we don't, it's not going to be added to the output stream. And if you're a C programmer, you're familiar with string contents always ending with a terminating null character. In assembly language, that is not something that happens automatically. If you want terminating null, you have to explicitly specify it. So we'll do that here by adding a /0. Now that should result in a null character being written into the output stream. But we won't rely on this because the write system call doesn't care about terminating nulls. You've already provided the length of the string, and it should be the first 7. Let's see, let's make sure we're in the right here again. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 characters. Those are the 13 characters of hello world message. So now we need to come up with a mechanism of determining where exactly the the message is. The message would be located at this address here, but it's an address relative to our this instruction here that let me start over. So we want to find out what the address of the message is, and the message starts here. Now in our previous examples, we've been able to count the relative address, but here we would need the absolute address of the message, because that is what the write system call needs. It needs to know where in memory this message resides. So we're going to have to start by counting the addresses from the beginning of our program. So this is address 0, 1, 4, no, sorry, 0, 4, 8, 12, 16, 20, 24, 28, 32. So the address of that message is actually at address 32. There we have it. So the next thing now then is to implement this define string function. So let's go ahead and do that. So define string takes a string. And so what we want to do now is convert that string to bytes. And if you're familiar with text in the C# environment, you know that a string is not a collection of bytes, it's a collection of characters. And those characters, when they get converted to bytes, uh, there's not a single way to encode the bytes of a string. You have to provide a specific encoding. We'll use the UTF-8 encoding to encode our string. So we will use encoding UTF-8 and we'll say get bytes. So this will give us the bytes that are contained inside of the string. And then we will write these bytes out to memory. And so we will introduce a memory.writeBytes where we pass in an array of bytes. And this will write them to memory. And then we have to update our pointer, which we've been calling inster pointer, by the length of those bytes. Like so. And I'm not sure why we're getting this error here. Ah, okay. It's a unsigned integer cast. The length of the bytes will always be a non-negative number, so we're safe casting to int. Now let's implement the writeBytes method. And the writeBytes method, what it is going to do is we also need to specify an address, of course. So let's give it an address to write to, and then we will do a array copy from the source array bytes at position 0 to the destination, this bytes at the destination address, bytes.length. That will write those bytes from the input parameter bytes to the member variable bytes. From the input parameter at position 0 to the member variable bytes at position address. Let's go back and add the address to here, like that. Let's build this. No errors. So our little program should now call the right system call. But we haven't implemented write yet. So let's go to our OS emulator and think about what that would need to do. So we would need to first implement a handler for the system call. When we would have to say, well, first give me the handle, which is in register 10. And then we need the address of the buffer. That's going to be in registers 11. And then finally we want the length. And that's going to be in the emulator registers 12. And then we're going to call a method called write to handle address length, like that. So where is this handle coming from? Well, it's an index into some form of data structure or an array of active handles. So maybe we need to create a list of such handles here. We'll create a private list of handles. And then we need to initialize this list of handles. But then we want to connect these handles to the C# runtime environment handles. How are we going to do that? Well, what we're going to do is we're going to be a little brutal and assume that we own the environment. And this code can later be changed. Of course, it's software, but for now, what we're going to assume is we're going to take over the console of the running program. So what we'll do is we'll say this console, whoops, dot out, close. We're closing the console output stream. We might as well close the input stream as well. And there's a third stream called error. We will close those three streams. And then what we'll do is we will open new streams to these three. But instead of using text writers, which is and text readers, which is what these three streams are, we're going to use the lower level stream abstraction of .NET. So what we'll say is that the in stream is going to be equal to console.open standard input. So now we have a stream of bytes connected to the standard input of our console. The out stream is console open standard output, and var error stream is console open standard error. So now we have three streams that we can put into our handles list. So we'll say this at handles, add input stream, and out stream, and error stream. And these are not integers, these are actual streams that we're putting in our list. So let's make sure we handle those accordingly. Great. So now we have set up the streams of our emulator. So now we need to implement write to handle. So write to handle, we'll first need to check if the handle is valid. So if handle is valid, let's use the handle valid convention where the is indicates a Boolean and we pass in a handle. If that's not true, then, well, then we have to return -1, which is a code for error. We're not going to be a fancy OS that tells you exactly why there was an error. We'll just say -1 to indicate something went wrong. So we will say return -1. Let's make this an integer function. And then when this executes, we want to put that in register 10. So we'll say emu.registers10 equals result, like that. If the handle is valid, though, then we're going to try to write to it. So first of all, we need to find the memory area where those bytes are located in, and that is address. So what we'll do is we'll say create a span of memory, which is memory dot, and we need the memory, don't we? So we need to pass that on to write to handle. We'll pass that in as an extra argument here. In fact, we're going to be using memory a lot, so why don't we pass in the memory as an argument to the constructor of this class? And that way, we don't have to pass it in as an argument to trap, and we will have it as an argument to our constructor, and we'll hang on to that. All right. So now we have implemented memory. Now we can say memory, give me a span starting at address address, and of length. And then we can take that memory and write to the stream at position handle. So we'll say handles at handle, and then we'll say write, and we pass it in a span. And if anything goes wrong, again, this is a sloppy emulator. We're not going to try to figure out what exactly went wrong here. We'll just report a general failure. Otherwise, we will report the number of bytes that we wrote, which is length. There we go. So now we need to implement isHandleValid to validate that we are using a known handle. So if the handle is out of range, then we can't use it. So if the handle is less than 0, or if the handle is larger than or equal to the list of handler count, then this clearly is not a valid handle. So you return false. Otherwise, if the handle slot is null, so we'll say var stream is equal to handles at position handle. Now if that is null, then it also is unacceptable. That should do the trick. So now we validate that the handle is correct. If it's not, we exit. Otherwise, we go ahead and try to grab a span for memory, and let's go to the getSpan method. And the getSpan is a read-only span, but we may need a writable one, so we'll change that to writable span. And we just return this dot bytes as span address length. Good. So let's review what we've done. In our main program, we have stored in memory a string, and then we're going to issue the system call write, passing in handle 1, which is the standard output, and then we're going to pass a pointer to our buffer, and then we have the number of writes that we want to write. After performing the write, then we exit the program. We're going to be brave and try running this. I'm not expecting this to work first try, but if we're lucky in the terminal window, we should see the string hello world. So let's go, give it a try. Oh, we have a failure. So let's fix that first. Oh, right, we need to pass in the memory now to our emulator, our OS emulator. There we go. All right, another shot. Still not building. What's the problem? Oh, right, we no longer need to pass mem. It's now a member variable. Let's go. Oh, we still have our test code from before. Let's get rid of that. So in fact, we can clean up this file quite a lot. Let's get rid of a few things. Let's get rid of this factorial function. We'll need the assembler. Get rid of this code for now. Here is our actual system call code. Let's get rid of all this, and this, and this. And then delete that. And the result is whatever comes out of the emulator now. And that should be the extent of our code. So does this look good? This looks good. Let's give it another try. Oh, and inside our debugging traces, we see hello world. A little underwhelming. Let's go and turn off the tracing so that we don't miss the glory of what we've accomplished, which is hello world without a terminating new line. Let's add the terminating new line just to make this cleaner. That will increase the length of our string to 14. And let's run that again. Beautiful. So we've reached a point now where we have a mini operating system. We're able to call system calls to it. And yeah, what else is there to say? This is it's pretty amazing. We're getting to a point now where we're almost ready to write some serious programs in our and targeting our little emulator. Because now that we have access to an operating system, we can now do things like open files, read files. We'll probably add a system call to allocate memory. And with all of those features, we can start doing my secret objective for the series that I won't divulge quite yet. But by having a fully fledged operating system underpinning our emulator, we can do some pretty cool stuff. So thanks for watching, and next time we will proceed with our emulator and maybe start doing a little bit of cleanup before the next phase. Thanks for watching.